Welcome to the General Chemistry 1 class. This section is organic compounds focusing on examples of polymers. In this lesson, we will explain the properties of some polymers in terms of their structure. Crystalline and amorphous polymers. Chains of polymers are bound by intermolecular forces called van der Waals forces that are relatively stronger than those present in smaller molecules. For chains to experience strong van der Waals forces, they must orient close to each other, i.e., there must be close packing among them. Moreover, the polymer chains are closely packed if they are arranged in an ordered manner. Polymers whose chains have a high degree of order are crystalline polymers, while those with less ordered chains are amorphous. Hardness of polymeric materials are affected by the strength of van der Waals forces existing among polymer chains. Crystalline polymers are hard and durable, while amorphous polymers are brittle. Crystallites. The given illustration shows how high-density polyethylene chains can be arranged. The chains encircled in red show the well-ordered chains, i.e., the crystalline portions of the polymer. These portions are referred to as crystallites. Effect of branching. Branching of polymer chains has an effect on the strength of van der Waals forces. Branched chains have weaker interaction toward each other, thus have less packing than linear polymers. The effect of branching explains why high-density polyethylene HDPE, a linear polymer, is harder and has a higher density than low-density polyethylene LDPE, a branched polymer. Effect of pendant groups. The pendant groups affect the polymer's crystallinity. Polymers bearing larger pendant groups may have low hardness compared to those with smaller pendant groups. Effect of tacticity. Isotactic and syndiotactic polymers are generally more crystalline as polymer chains can have regular arrangements. Atactic polymers are usually amorphous. Melt transition temperature. As temperature is increased, van der Waals forces may be disrupted, making polymers less hard. At this state, the crystalline nature of polymers become amorphous. The temperature at which this state starts to occur is called the melt transition temperature, Cm. This temperature is just like any molecule's melting point, at which a solid substance starts to become liquid. Glass transition temperature. Amorphous polymers are hard and brittle like glass. At increased temperatures, such polymers can become soft and flexible like a rubber. The temperature at which a polymer transitions from glassy to rubbery characteristics is called the glass transition temperature, Tg. Major classifications of polymers. Polymers can be classified as thermoplastics, thermosetting resins or thermosets, fibers, and elastomers. Thermoplastics. Thermoplastics, or simply plastics, are characterized by being hard at low temperatures and soft when heat is applied. The process is reversible. They harden as temperature is lowered. HDPE, LDPE, PP, PS, and PVC are examples of thermoplastics. Thermosets. Thermosetting resins, or simply thermosets, are polymers that do not flow or soften upon application of heat. In fact, too much heat may lead to their decomposition. Thermosets are hard materials owing to the presence of crosslinks, a small group of atoms covalently linking polymer chains. The presence of crosslinks renders thermosets to form a big molecule called a polymer network. The presence of crosslinks restricts the polymer chains from moving freely even when heated. Thus, thermosets can never attain the state of melting. Urea formaldehyde resin is one example of thermosets. It is prepared by heating a mixture of urea and formaldehyde. One use of thermosets is for laminating different objects. The glass-like material in the illustration is an example. Fibers. Fibers are thermoplastic polymers produced a process called extrusion in which the molten polymer passes through a small hole. Upon cooling, the extruded polymer is stretched or drawn stretched until the desired strength of polymer is achieved. During the process of drawing, the polymer chains are brought to a highly crystalline state. Extrusion is done in manufacturing threads and strings made from polymers like nylon, polyesters, and polyethylene. Elastomers are amorphous polymers that can be stretched and elongated but goes back to its original state once released. The requirements for a polymer to be an elastomer are 1. It must have low glass transition temperature, 2. Small degree of cross-linking to somewhat hold the polymer chains together, and 3. Disordered polymer chains. Elastomers. Natural rubber is a common example of elastomers. It is a polymer of isoprene in which the methylene (CH2 negative) groups lie on the same side of the alkene during polymerization as shown in the given structure. The given illustration shows the collection of latex from a rubber tree. Latex is then processed to obtain a natural rubber. To summarize, arrangement of polymer chains dictates the properties of a polymeric material. Polymers with high degree of order of polymer chains are crystalline, while those with less ordered chains are amorphous. Polymers can be classified as thermoplastics, thermosets, fibers, and elastomers. This is our bibliography for further readings, and that would be all. Thank you. Now that we are done with the discussion, let us assess your knowledge through a short quiz. And we are done. Congratulations and thank you.